Welcome to our April webinar. Good to see so many of you joining. I'm Jackie, Marketing Manager at Senceive. We're now part of Edify Remote Monitoring Solutions. It's my pleasure to introduce you to Sadaf, a product analyst here at Senceive. She's been involved across product strategy and development, as well as real-world testing in North America. And today we're really lucky because she's going to talk you through some of our new exciting developments in track monitoring. As always, please feel free to send in the questions throughout the webinar into the question box, and I'm sure we'll have some time at the end to go through some of them. Sadaf, thank you so much for joining us today. I'm going to turn it over to you now. Thank you so much.
Thank you, Jackie. Hello, everyone. Welcome to today's webinar. We will be talking about what's new in track monitoring with a focus on advancing accuracy and insight. I'm going to start with a brief introduction on myself. My name is Sadaf Shafi. I joined Senceive in January 2024 as a product analyst. My focus is rail within the North American region. I'm also a member of ARIMA technical committees. Actually, my involvement with ARIMA started as a student member, and now I've been a member of 2 technical committees since 2023. I have a master's in civil engineering from University of Illinois at Urbana-Champaign. During my master's, I've also worked as a research assistant at RailTech, focusing on railway infrastructure. And I also hold a bachelor in civil engineering from my home country, Iran. So today we will be talking about trackbed monitoring. I'm going to start with a high-level introduction on Senceive, and then we will narrow it down to our trackbed monitoring solutions. And then we'll talk about our rail-mounted tiltmeter, which is our newly released product. I'm going to talk about some of the tests we've done as part of the development effort on this project. And then we will talk about FlexRail, which is the other addition to our trackbed monitoring solutions. And we will end the session with a Q&A. Starting with Senceive, we are a provider of wireless monitoring solutions. Our focus is supporting civil engineers in maintaining the safety and reliability of infrastructures. We were founded in 2005 and are now part of Edify Technologies. Our headquarters in the UK. We have additional offices in the US and Australia, which gives us a strong global presence. With more than 120,000 sensors deployed around the world and in all 5 continents, we offer 24/7 customer support and work closely with our clients to deliver reliable data and insights that help them monitor and manage their assets effectively. Our wireless solutions are used in different applications, as you can see here on this slide. This includes rail, which is one of our most important major sectors. We also help engineers in monitoring and maintaining bridges and tunnels, structures, highways, geotechnical, construction, energy, and drainage systems. Today's webinar is only focused on rail, however. Moving on, I'd like to also give a high-level overview of our solutions from hardware to data and support. Starting on the left side of the screen, our core products include our triaxial tiltmeters, ODS sensors, which is our laser-based optical displacement sensor, and camera systems. These are designed to monitor movement and structural behavior in real time. Moving across, we also support third-party integration. Means our system isn't limited to Senceive sensor, integrate with other instrumentations and allow our clients to bring different data sources together into one platform. We also have our network capabilities, which is one of our main strengths. We offer two main options, flat mesh and GeoWAN. Flat mesh is typically used for dense sensor deployments when you need high frequency data readings and responsive and intelligent communication between the nodes. On the other hand, we have GeoWAN, which is designed for longer range applications up to 15 kilometers or 9 miles of range, which makes it ideal for cases or assets that are more widely located. And finally, on the right side, we have our software and support, which includes our data management and visualization platforms, Senceive.io and WebMonitor, where all the sensor data is brought together, analyzed, and presented in a user-friendly way. Alongside that, we also provide customer support, training, and services to ensure systems are running effectively. Here we have a selection of rail asset owners worldwide who have trusted us to deploy our systems and sensors on their assets. Across North America, Europe, Australia, and other regions, we help a wide range of operators from major freight railroads to passenger transit authorities and metro systems with different rail environments, different standards, and obviously different operating conditions. Given this diversity, we're committed to continuously upgrading and improving our products to make sure that we meet the evolving needs of our clients and perform reliably across all these different use cases. Moving on, I'm going to talk about our trackbed monitoring solutions specifically. So our trackbed applications can be categorized into three main categories. The first one is track geometry, where we measure cross-level, twist, lateral alignment, and vertical alignment. The next category is earthworks, where we help clients monitor their slope and embankment stability, landslide and washout, as well as rockfall events. And the third category is railway structures, when we help our clients monitor tunnels, overhead line equipment, as well as bridges. To put all these into context, in the next 3 or 4 slides, I have just some examples of what these means in actual cases. Starting with track geometry, at the most important, I would say, use case is when construction is happening near or under the track, adjacent construction, or for example, grade separations. These are activities that are happening next to or under an existing track, and the asset owner wants to make sure that whatever is going on near their track is not affecting their safe operations. And on the other hand, the contractor or the company who is doing the work wants to make sure that they can proceed with the speed that they are conducting their work. This also includes activities that happen under the track, for example, under track pipe ramming or culvert replacement and construction. On the lateral movement side, we can assist with identifying track buckles as well as monitoring curve breathing over long periods of time. And on the earthwork side, just want to include some photos of landslide and washouts and emphasize that these usually occur in remote locations where access is limited or can be limited once these occur. So it's important for the clients to make sure that they have systems that are running and giving them data regardless of people being present on track. Now I'm going to talk about what products do we actually offer for doing all these measurements and monitoring. Our main product for our trackbed solutions is our wireless triaxial tiltmeter. Next, we have the rail temperature sensor, the ODS, which is our laser-based displacement sensor, which also comes with a built-in tilt sensor in it. and also a solar powered gateway, which allows the communication of all the sensors in the monitoring zone. As part of the parameters that each of these sensors measure or help with, the rail temperature one is pretty straightforward. It measures the temperature of the rail, which is useful for buckle applications. For with Tiltmeter, we can measure cross-level, twist, and longitudinal profile. I'm going to get into way more details about these in a few minutes. And ODS helps measuring lateral displacement of the rail. Talking about deployment options, ODS, I'm going to start with ODS and then we're going to talk about Tiltmeter because that's the majority of the content for today. But starting with the more straightforward one, which is the ODS, it can be deployed in two different ways. You can either mount it on a stable pole off track and point at the web of the rail, and it's going to give you the changes in the distance between the sensor and the rail. In other words, if the rail moves laterally, you can have access to the actual magnitude of that movement. The other deployment option is kind of the opposite. You can mount the ODS on your sleeper and point at a pole that's stable. So in this case, in both cases, the pole needs to be stable, and then we have a moving object, and we can measure the change in the distance between the two or the displacement. Moving on, before I get into why we're talking about rail-mounted tilt and all that, I'm just going to start with some definitions. The two major track geometry parameters that we measure using our tiltmeters are cross-level and profile. I did not include twist here because twist is very relevant to cross-level. So definition-wise, cross-level is the difference in the elevation of two rails at each section of the track. And profile is the surface uniformity of each rail in the vertical plane over a predefined length. That predefined length varies from region to region. So if we're in Europe or UK or in the US, these lengths are different, but the concept is the same. Okay, how do we do it? How do we measure it? We usually mount our tilt meters on the sleepers, and then that allows us measuring the rotation of the sleeper, and then we take that measured rotation and calculate the displacement using basic trigonometry. As you can see here on this slide, we multiply the tan of that measured angle by track gauge, and that gives us the cross level. If this value is taken from the zeroed baseline, that gives us a relative measurement, but it can also be applied to actual survey readings, and that can make us closer to the absolute cross level value. The other parameter is vertical profile, which is a little more complicated from cross level. However, the concepts that we are using are pretty much the same, but then it becomes a little more complicated because we use a chain or array of sensors to create a profile of the rail, and that gives us an indication on whether the surface uniformity has been maintained or if the track is dipping or humping. The way that we do that, the first step is the same as cross level. We multiply the tan of that angle that's measured using the tiltmeter by the distance between the nodes, what we call the virtual beam length. And then we accumulate all these vertical displacements along the chain, and that gives us the vertical displacement at any given point in that chain. The important thing here is that we need to make sure that we are between two fixed points so that we can apply our corrections into the chain and make sure that the data is reliable. Moving on to rail-mounted tiltmeter, before I start the next part of this webinar, I would like to emphasize that what I just discussed about using sleeper-mounted tiltmeters for measuring profile proved to be reliable and accurate in most of our use cases on the east of the Atlantic. But in the US, what we've realized is that we faced some challenges. And those challenges are mainly because the tracks, the railway tracks in the US and for example, in the Europe, are basically designed and constructed for two different reasons. In the Europe, the railway tracks are mainly built to move passengers from point A to point B. That means higher speed and lighter trains. In the US, however, the predominant use case for railways is to move freights from point A to point B. And what that means is that the trains are much heavier here and a lot slower. Therefore, the tracks are designed in a way that allows that those heavy loads to be moved. And that, as part of that design, some level of flexibility is introduced to the track through the use of timber sleepers, as opposed to concrete sleepers that are mainly used in Europe and UK. Uh, Another thing that's different is the type of fastening systems that's used to attach the rail to the sleepers. In the US, again, the predominant type of fastening systems for timber ties are tie plates and cut spikes, which when we compared that to the typical fastening systems that are used in concrete ties, they are not as rigid, so they have less rigidity. What this means is that when we use our sleeper mounted sensors here in the US and trying to derive a profile out of the rotation of the sleeper, we usually see large movements that are not actually representative of the rail movements. The ties, to an extent, move independent from the railways, and because all the track geometry parameters based on the standards, they need to be measured from top of the rail. When we are measuring the movement of the sleeper and assuming that the rail is moving the same way, that becomes a challenge. With that said, we looked into developing a tiltmeter or a bracket that allows us to mount the tiltmeter on the rail directly. This helps us to remove any doubt about the rigidity of the connection between the sleeper and the rails. And in other words, it allows us to measure the rail movements directly. As part of the development process, I'm going to talk you through the testings we've done to check the accuracy, as well as our survivability testings, which was done in the lab and in the field. The first thing we did was to perform a proof of concept testing, which we actually worked with a third party because we wanted to make sure that we are using an objective assessment as opposed to any sort of bias that could be introduced to the results if we were to do it ourselves. So what the third party helped us to do was to compare the accuracy of profile readings, specifically when tiltmeters are mounted on the sleepers versus when they are mounted directly on the rail. The location of this test was a secondary track with low traffic in Illinois, USA, obviously. And what we tried to do was to make sure to pick a location that to an extent represents the actual mainline tracks here in the US. So we made sure that it's timber ties with the type of fastening systems that I just mentioned. And another important things about this location was that the ballast support was not great. So there were like some missing ballasts in certain locations of the track. So we wanted to see if the track condition is not perfect, and also we are working with the components that are the most common ones in the US. Is there a difference between the rail mounted and sleeper mounted sensors in terms of accuracy of profile readings? As for the scope, we mounted 54 sensors on the sleepers and 54 directly on the rail. And then the track was lifted using a jack to introduce profile deviation to the track. And then manual survey was taken after each lift of the jack to serve as the ground truth for the comparison. The results were pretty interesting. What we saw was when we compared the tie-mounted sensors results with the rail-mounted sensor results, we saw an 86% improvement in accuracy. What you are looking at in this graph here, it's a comparison of our rail-mounted sensor results versus survey. The x-axis is the position of the track, so the center line was when the jacking occurred. Here was when roughly where the jacking took place, and then these are the fixed points at the two ends, and then each of these are one lift of the track. The dashed lines of our measurements and the solid lines are survey readings. As you can see, there's a very close agreement between our results and the ground truth for this test, especially in lower elevations. When we go higher than certain levels, higher than 2 inches, we can see some differences, but it's very important to note that those type of movements are not expected for the types of use cases that we talked about. For example, in the adjacent construction that I mentioned is one of our main use cases. The thresholds are around 1/4 of an inch. So these are the type of movements that we expect to see, which we saw great agreement in magnitude and trend between the rail-mounted results and the surveys. This gave us the confidence to go and actually develop this product in a way that it can be used on the main lines here in the US. That came with its own challenges. The main challenge with that was that when you take a sensor from the sleeper and mount it on the rail, you are getting closer to the interface of the rail and the wheel. And what that means is that the levels of vibration and shock that the sensor experiences and must withstand in order to reliably measure the parameters increases by orders of magnitude. Therefore, survivability aspect became the important and I would say most important factor at this part of our efforts. What you're looking at here is a 3-stage process that we used for ensuring the survivability aspect for the rail-mounted tiltmeter. Starting on the left, we begin with the concept, modeling, and lab testing. This is where the idea is first developed and tested in a very controlled environment to make sure that we can validate the concept and refine the design if needed. And if it meets all the minimum requirements, then we can move on and perform in-track testing. The in-track testing is a more realistic environment. It's a semi-controlled environment, not completely controlled and not completely similar to the actual live environment. It's semi-controlled and allows us to check the performance of the sensors in a more realistic environment, and we can see how it performs under conditions that resemble actual operations. It helps us further evaluate the reliability of and performance of the sensors and their survivability, obviously. And if anything doesn't perform as expected, we go back to the design stage, make some changes, and then redo the process. If the semi-controlled testing is successful, then we move on to revenue service testing and implementation. This is where we mounted the sensors on an actual live revenue service track. And we can see at this point, we're looking at how it performs in real service, how users interact with it, and how it impacts the operations, if it does, and whether it delivers the expected outcomes. The one important thing about this process is that it's not linear. You can see the arrows forming a loop, which means that allowed us to continuously refine and optimize the system over time. So what this represents is that it's a structured yet iterative approach for development that we used for this product. With that said, I'm going to walk you through all the testings that we've done to ensure the survivability of the sensors. The very first round of testing that we did was a lab test. After the proof of concept, our engineers designed a new bracket that allowed us to mount our high-G nano macro tilt meters on the rail directly. Then we tested those brackets and the sensor obviously in the lab. What the sensors were tested against was vibration and shock. This is important to make sure that we're talking about two different things here. Vibration simulates the constant vibration that the sensor and its mounting brackets go through whenever a train is passing. And the purpose of the test was to assess the assembly's ability to withstand that. Shock, on the other hand, was used to simulate any sorts of impacts, which are also another type of loads that are expected in the railways, and especially in certain areas, for example, near joints or near fixed structures. It can have many different causes, but those are also a very expected demand on the sensors that we wanted to make sure that we account for. What we did after that lab test was some changes were introduced to the hardware based on what we found, and at that point we moved on with our semi-controlled environment testing. That second step of the process. For this one, we use the MXV's FAST facility. FAST stands for Facility for Accelerated Service Testing, which was amazing for our need because we wanted to make sure that we accumulate enough tonnage to help us evaluate the survivability of the sensors over long terms. And what this facility does is that they run trains over and over and over. So the amount of tonnage that we accumulated during the duration of this test, which was 6 weeks, is actually, it's going to take much longer to accumulate that amount of tonnage on an actual railway location. As for the scope, we tested 150 sensors with two different mount types that you can see here, the bracket and clamp, which was newly designed specifically for this application, as well as another mount type, which we glued the sensors to the web of the rail, as opposed to the other one, which the sensors sit near the base of the rail. We tested the sensors on different sections of the fast loop, including sections on tangent track, curved track, as well as sections with timber sleepers and concrete sleepers. Another thing about MXV's fast loop is that they run overloaded trains there, so the axle load coming from each axle of the trains is actually higher than what we would expect on actual revenue service environment. Over 6 weeks, we accumulated 30 million gross tons, and that was a very important step along the way for our developments. But the main finding out of this test was that we realized that we needed to introduce some sort of shock dampening mechanism to our brackets. I'm going to get into a little bit more detail about that in the next slide. So what we did was we installed some shock loggers on the rails and at 4 different locations, and measured the shock in 3 different axes, X, Y, and Z. Uh, Interestingly, we saw very high levels of shock up to 150 G present at all 4 locations, but that apart, another thing that we found out was that a constant level of around 25 G was present at all time during the train passes. So we learned here that we needed to introduce those shock absorption mechanisms to our brackets. And that's what we did. Our engineers designed changed the design in a way that we added specific pieces to make sure that we account for that shock. And then we went back to the lab and tested the different brackets with these shock absorption mechanisms to rate their effectiveness in terms of absorbing the shock. We tested them for both positive and negative shocks, as you can see here on these photos, that's what they mean. And the results were interesting. Both of these both of the mount types that we tested, they showed better performance compared to what was used at the MXV test, and we realized that the efficiency of these brackets is different depending on the direction of the shock. After that, we went to perform revenue service testing on an actual major class 1 track here in the US. We are very grateful for our partners who allowed us to use their tracks for our long-term testing. They allowed us to mount 150 sensors on one of their very busy main lines with high traffic and high tonnage, expected high tonnage. The sensors were mounted there in September 2025, and they are still there. So right now, I think we're somewhere around 8 months of long-term survivability testing. Another interesting thing that we encountered on this live track that we did not encounter at MXV was because of the duration of the test was so long and the specific location of this test, we had very huge variations in temperature. The temperature actually dropped down to minus 20 degrees at some point with snow present. So the nodes were to an extent buried in the snow, and we were able to monitor their performance during those harsh environmental factors as well. We used the same sensors that we used at the MXV facility. So 30 MGT was accumulated there. And here we also accumulated around 25 MGT, which puts us at 55. I did not include that, but according to a study done by AAR in 2008, about 80% of the track miles in the US have an annual accumulated tonnage of less than 60. Therefore, that puts us in a good spot in terms of assessing the survivability. We were happy with how the sensors performed. We had some minor updates that needed to be implemented to the brackets and their assembly process, but overall, this test gave us the last level of confidence that we needed before going and releasing this new brackets and products. I would also like to mention that this test is still active. We're still accumulating tonnage and monitoring the performance over seasonal exposures. So what's new in track monitoring right now is we are offering 2 new brackets that lets us to mount the nano macro high G directly on the rail for better profile measurements. The one bracket, as you can see on the left side of the screen, is the vibration pad bracket, as we call it. It comes with a slightly higher cost, but according to what we saw in the lab tests and also in the field tests, we believe that this one has a better shock absorption capability. The other mount type that we are releasing is the right angle and glue, which gets glued to the web of the rail, and it's slightly lower, not slightly, it's lower cost and medium survivability. By medium survivability, I mean it's up to the users to decide which one they want to use, but we would recommend, depending on the location, for example, if you are at location where high vibrations or high shock levels are expected, it's best to use the vibration pad one. However, as for there are some differences in the installation part. This one is faster, this one is slightly takes longer to install, so they come with pros and cons. Another thing that I mentioned in the two slides before was the temperature variations. And what we realized was that when we were using tilt-mounted sensors, the temperature effect on the data becomes more pronounced. I would like to mention that tilt meters always, they exhibit some level of temperature dependency in their results. So that means that we can see temperature related fluctuations in the data. That introduces some challenges to the users because we are talking about very high resolution sensors, and they take the slightest change in the position of the asset that they're monitoring, and that gets reflected in the data. And sometimes it becomes difficult to distinguish between the type of the movement that you're seeing, to distinguish if this is temperature related or if this is actual true structural movement. To address that, we added a new feature to our data visualization platform, WebMonitor, the temperature correction feature, which allows the users to use a regression-based method to remove this temperature-related influence on their data. The users can pick between linear fit or second degree fit, or they can also do it manually and then add the parameters here, and the system automatically applies that to historical data as well as on any data that's going to come in the future. It also lets the users to use R squared metric to assess the quality of the fit and help them decide which one to use, linear or second degree, or even either to apply it at all or not. So the result would be a clear view of the actual structural movement and improved confidence in data interpretation. And now I'm going to move on to FlexRail, which is the other addition to our trackbed monitoring solutions. FlexRail is a void meter that's manufactured by Sysgeo. We are all under the remote monitoring of Edify technology. Um, FlexRail actually automatically measures the maximum deflection of the rail when a train is passing. It is now fully integrated into our Geo1 platform. It has a technology called SPV, which stands for Start by Vibe. And that does is that it wakes up the sensor when a train is passing, and it only takes readings when the train is passing and stops take readings when the train pass ends, and then it saves the maximum deflection measured during that train pass. It can also be equipped with biaxial tilt meters or inclinometer to measure rail tilt in two axes parallel and perpendicular to the rail. We are going to have a webinar soon specifically focused on FlexRail. So here I'm just going to very briefly discuss it. Getting a little bit into more details of how it works. Obviously, this is another wireless solution added to our broader portfolio. The standard, it uses two batteries, disposable batteries, and then the standard design allows for installation on the rail with a foot length of 140 millimeters, but it can be extended up to 150. 150 millimeters supports 136 RE rails, which is the the one that's usually used for freight rails, and that's larger than the ones that are used for passenger rails. Like I mentioned, it allows dynamic vertical displacement measurement. And by dynamic, I mean it takes 350 readings per second when a train is passing. And then the static tilt measurement is regardless of that SPV technology. It can take readings on a predefined schedule. So you don't need a train to pass to take those tilt readings. It is currently available on 868 hertz band, but we are working on the other versions to support more frequency bands. And I would like to conclude with a summary of what we are aiming to do. Our aim is to deliver robust, reliable, and practical solutions, sensor-based solutions to help infrastructure owners and contractors to better manage and monitor their rail infrastructure. Our focus is to make sure that our sensors are easy and fast to install, especially when we are in the railroad operational environment where every minute matters. We make sure that our sensors, our trackbed sensors, do not rely on line of sight. I'm talking about the tiltmeter specifically. And then that means that frequent follow-up site visits for maintaining the sensors are minimal, if not zero. And I would also like to mention that the system is designed to complement the existing measurement and monitoring systems in places that those systems have limitations. For example, at very high risk locations or hard to access areas, or where time restrictions are very important. And at the end of the day, we want to enable our users to make better informed data-driven decisions in a faster way. And we continue to improve and expand our products to support more regions, more parameters, and FlexRail and rail-mounted tiltmeter, I believe, are an example of our commitment to that. So with that said, I would take questions if we have any.
Wonderful. Thank you, Sadaf. That was really interesting. I mean, all of it, especially all the behind the scenes testing that you were showing with the rail mounted tilt. Particularly enjoyed that. We have two questions coming in now, but if you have questions, please feel free to put them in now. The first one was about data frequency. So he's asking, what is the frequency reading of the sensors? Can users change that, and can they do that remotely?
Well, the frequency, yes, it's customizable by default. The tilt meters take readings every 30 minutes, and that gives the maximum battery life, but the users can change that. It can actually be lower to down to minutes or even seconds. But it's important to note that if we go under a minute frequency, that compromises the battery life.
Makes sense. Okay. The next one is about cellular coverage. So this person is asking about really, really remote areas that might not have cell coverage. What can we offer in this situation? Can we do anything here?
Uh, yes, actually, we one of the other product releases that we have very recently is actually we can now offer Starlink. So in those locations that cellular coverage is not available, we do now support Starlink, and that allows the users to use our systems in those areas.
Wonderful. Great addition to the portfolio. What about using glue? Someone is asking, if you install a sensor with glue, is it reusable after that?
So the brackets are designed in a way that you can remove the sensor. It's actually a two-part attachment, so you can remove the sensor, but the right-angled bracket remains on the web of the rail. You can actually remove that using some other means, for example, with some more force, but the sensors can easily be removed for example, if maintenance is going on or any sort of disturbance is expected, the sensors can be removed.
Wonderful, that's good. Um, Someone's asking what is the differential between concrete sleepers and timber in the tests that you conducted? Is it worthwhile to utilize the rail clamp mount versus adhesive on concrete sleepers?
So we actually didn't see that much of a difference in terms of survivability of the nodes in concrete and sleeper sections of that test. It was pretty uniform on that test that we did. The second one that we did was only timber ties, so I don't have any comparison from the
Yeah.
second one.
And how do the cross-level results compare with the tie mount versus the rail mount on timber ties?
Okay, that's actually a great question. I should have mentioned this earlier, but what we saw, if we take the nodes from the sleeper and put it on the rail, even though it gives us a very significant improvement in profile, it actually comes with a compromise in cross level. So for cross level applications where cross level is the key factor, we still recommend using sleeper mounted sensors. The tie mounted ones or the rail mounted ones are specific for vertical profile measurement.
Makes sense, yeah. Another one is, do you utilize a notification system when a rail movement passes a threshold?
Yes, so that alert system is identical to our sleeper mounted sensors, or basically all of our other sensors. Alerts can automatically be generated and sent to the users via text or email
Right,
in,
great.
in case of a threshold exceedance.
Mm, right, so they're notified right away. If we have to install a sensor every 4 meters, which location do you suggest to install? The middle of the track or on the side of the sleeper?
Every 4 meters for cross level, I'm assuming.
Hmm, probably.
Well,
Doesn't
I would
say.
say that depends on the type of sleeper that you're working with. Uh, we usually, to avoid safety hazards, we usually recommend mounting them on the side of the sleeper. But if it's concrete, I would say it really doesn't matter that much because concrete sleepers are rigid by design, or they're supposed to be rigid. But for timber ones, I would say side.
Thank you. And this is a WebMonitor question, but can Senceive provide daily auto-generated reports covering the movements of each sensor in a 24-hour window?
Um, I believe we should be able to do that because I know our customer support team work on customized reports for each of our customers based on their projects. So I
Mhm.
would say yes. It's not my actual area, so I'm not as confident answering to this one, but I'm
Mm,
pretty sure they should be able to do that.
wonderful. I think I've covered most of, or all, hopefully. I think there was an overlap in a few of the questions. And I think we're out of time, but of course, if I didn't ask your question, please email us at info@senceive.com. And please look out for our colleagues at Hugenberger and Sistio are doing a dam webinar at the end of May. So if you're interested in dam monitoring as well, look out for that on their social media. Sadaf, wonderful to have you. Thank you so much. Really informative webinar.
Welcome.
And thank you so much, everyone, for joining. And look out for our next one. Thank you, everyone.
Thank
Have a
you.
great rest of the day. Thanks, Sadaf.
Bye.
Bye. Bye.